During this video, you will learn about the combined score and find out how to aggregate expert opinion in the classical model via a decision maker. During the previous module, we saw how experts' performance can be objectively measured within the classical model. The two measures are the statistical accuracy, or the calibration score, and the information score. Consider an example with three experts. Expert 1 has a poor statistical accuracy but is very informative. Expert 2 is more statistically accurate but less informative, whereas Expert 3 is quite informative and somewhat statistically accurate. Which expert do you think performed best? Of course, we don't want to answer this question just by using our intuition. So we propose a combined score, that is the product between the statistical accuracy and the information score. For the three experts in our example, we obtain the following combined scores. Expert 2 has the highest combined score of about 0.3. The combined score of Expert 3 is quite close, of 0.21. Expert 1 has a very low combined score of 10 to the power minus 6, which is due to the very low statistical accuracy. So note how the combined score is actually driven by the statistical accuracy. We can now objectively evaluate experts' overall performance. The combined score not only allows us to investigate the performance of the experts, but also enables us to aggregate expert opinion. The weights used in combining experts' assessments are based on the combined score. These are called performance-based weights. The weight of each expert is determined in the following way. Assume there are n experts. Then the performance-based weight of expert I is given by Wi, which is the ratio between the combined score of expert I and the sum of the combined scores of all experts. Note that the weights are normalized. That is, the sum of the weights of all experts is 1. Let's take another example with two experts. From multiplying the statistical accuracy by the information score of each expert, we obtain the combined score. The weight of expert 1, W1, is obtained by dividing the combined score of expert 1 to the sum of the combined scores of both experts. We obtain W1 to be 0.12. Similarly, we obtain the weight of expert 2 to be 0.88. We see how the weights of the experts reward good overall performance and in particular good statistical accuracy over high informativeness. These normalized weights allow us to combine experts' distributions, either the probability density functions, denoted by small f, or the cumulative distribution functions, denoted by capital F. So the classical model proposes a weighted averaging model, or a performance-based linear pooling. Note that the combined distributions also result in a distribution, since the weights are normalized. The combination of experts' assessment is often referred to as decision maker. Please note that in this context, a decision maker represents a mathematically calculated distribution, which corresponds to a virtual expert. It is assumed that the real decision maker would adopt this distribution as their own. The density function or the cumulative distribution function of the decision maker are therefore linear combinations of experts' density or cumulative distribution functions. As we have seen these two examples, strong weights reward good expertise in uncertainty quantification. This expertise will be passed on to the decision maker, as we will see during this module. Here is an example of cumulative distribution functions of two experts, in blue and green. The weights of the two experts are 0.12 and 0.88, and they lead to the cumulative distribution function of the decision maker in red. We see how the distribution of the decision maker is mainly determined by the distribution of expert 2, due to the high weight of this expert. and slightly pull down or up in places, which reflects the contribution of expert 2 to the decision maker. Consider now another example with 7 experts for which we record their statistical accuracy and informativeness. Recall that the statistical accuracy is the p-value of a hypothesis test, where the null hypothesis is that expert assessments are statistically accurate. In practice, a p-value smaller than a given significance level provides sufficient evidence to reject the null hypothesis. The significance level is typically chosen to be 0.05. So a calibration score smaller than 0.05 would be sufficient to reject the hypothesis that expert assessments are statistically accurate. We can then restrict our attention only to the experts whose statistical accuracy is at least 0.05. We see that expert 1, 4, and 6 actually meet this requirement. Just as in the classical hypothesis testing, this threshold is arbitrarily chosen and any other value could be chosen in practice. We consider this threshold in the calculation of the performance-based weights. We therefore introduce a significance level, alpha, which needs to be positive and smaller than the largest calibration score. An indicator function will take the value 1 if the statistical accuracy is greater than the significance level alpha, and 0 when it's not. When the statistical accuracy of an expert is greater than alpha, then this expression reduces to the combined score of the expert. If the statistical accuracy is smaller than alpha, then this expression is 0. This expression is called the scoring rule. Theoretical results for the classical model are available to prove that this scoring rule is an asymptotically proper scoring rule of averaging distributions. Roughly speaking, this means that an expert achieves her or his maximal expected weight by, and only by, stating assessments in accordance to her or his true beliefs. This scoring rule gives us another set of weights which depend on alpha and which allows us to select the experts used in our linear pooling by using this threshold alpha. Note that when alpha is 0, we retrieve the weights introduced before. Finally, we can use the newly obtained weights, which depend on alpha, to aggregate experts' distributions. The decision maker density or cumulative distribution function will follow. How would you choose the values of alpha? Can you think of an optimal way to do that? You will find out more about this during this module. Thank you for your attention.